Hi everybody. Just so you know, we're going to do a half-hour Q&A at the end of the show. For those of you that want to stick around, feel free to enter questions in the Q&A as they come up, or save them to the end. And then whatever, if there are questions we can't get to, we'll answer them through our Twitter feed at Carleton Science over the next day or so. Okay, thanks. All right. Welcome, everybody, to the 14th Annual Carleton University Chemistry Magic Show. On my right, I have our professor from our department and the chair of our department, Bob Blow It Up Burke.
Hi, everybody.
And my name is Jeff Magic Manthorpe. And in case you're wondering what the heck we just did, well, here's a very small repeat. Woo! Okay, so what that was actually some streamers that you would put up at a kid's birthday party. Okay, and you can see, doesn't look that different, right? But what we actually do with those streamers, when you buy them, it says that they're actually flame resistant. I forgot to save some because this is just too much fun. But yeah, clearly we've altered it. So you can see there's no smoke, no ash, nothing left. And the reason that burns that cleanly is we've put extra nitrogen and extra oxygen in it. So now it doesn't need oxygen from the air to burn, or it doesn't need nearly as much. And by releasing nitrogen as well, it comes out as nitrogen gas. Now that actually increases the amount of energy. So that's why something like toluene, which is an organic solvent, doesn't burn very well. Okay, it's very smoky. But if you put extra nitrogen and extra oxygen in, you get trinitrotoluene, better known as TNT. Now, fortunately, this doesn't burn that well, as well as TNT, because otherwise,
we wouldn't be here.
We wouldn't be here, Change my nickname to Napoleon Blown Apart. Now, if you want to see this demo again, here we go. One more time. Woo! Let's try that again. Okay, here we go. All right. So that's nitrocellulose, or better known as flash paper. What do you got, Bob?
Good stuff. I want you to watch the front 5 beakers here. I need your help, Jeff. And we're going to pour the back ones into the front ones. And this is called a clock reaction because these things have different concentrations. 3, 2, 1, go. And therefore react at different speeds. So don't take your eyes off these front ones. Watch them all. There's one. Now the next one has a lower concentration. Lower still, so it goes more slowly. Lower still. There we go. And the last one's the lowest concentration. So that one takes the longest. There we go. So you can alter the rate of a reaction by altering the concentration. We're going to see other examples of that today. What do you got, Jeff?
Okay, well, with the holidays coming up, we've got a few Christmas-themed demonstrations coming up, but, we figured we might as well go back in time and have a little bit of fun. And, this demonstration is actually called the Halloween reaction. So Halloween colors are orange and black. And so what we're going to do is we're going to have a delayed reaction like this clock reaction that's going to be orange and then black.
Whoa, nice orange.
And black.
There we go.
Okay.
Great colors.
Right. Cheers.
Yeah, cheers. See how long you last.
Yeah. Well, not very long, because the orange color actually comes from mercury iodide. So that would be mercury iodide.
All right. This is called an oscillating reaction, which means that it's going to oscillate back and forth. So it starts out clear. If I add these two, you get a kind of deep yellow color. But don't take your eyes off it because it's going to do some interesting things. So it's turned blue. That's the same iodide starch reaction that caused the first ones to turn blue. But this oscillates. There's a system of 5 reactions here which compete with each other. And one overwhelms the other, and then the other overwhelms the one. And so these reactions go back and forth between a yellow and a blue color. And that'll continue to oscillate for maybe 20 minutes, something like that. It'll oscillate, I don't know, dozens of times. It's quite a complex system of reactions. It takes a little while to make up these solutions. But I think you'll agree that's a pretty cool effect. So that's an oscillating reaction. What you got?
Well,
I got.
Why don't we make some noise?
All right. If I can get this out of here without it going off. There we go. Thank you. I'll draw your attention to these 3 pieces of filter paper. And I'm putting it down very gently. You can see there's a bit of a purple stain on each piece of filter paper. And that purple stain is nitrogen triiodide. And this is a very unstable compound. So it takes very little energy to make it decompose. And when it does decompose, if you have 2 of these, you'll get a nitrogen and 3 iodines. And both of these are gases, whereas the nitrogen triiodide is a solid. So we go from a solid to a bunch of gas, big expansion, and that's what you perceive as an explosion. So this sort of pops, but it's interesting the way it does it because it takes very little energy to make it, to set it off. All I'm going to do is touch one of these with this spatula. And when one gets set off, the shock wave from that is going to set off the second one, and the shock wave from that will set off the third one. So watch carefully and watch for the purple cloud, because the purple cloud is the iodine gas that's released. All right, here we go. Just going to touch it. Oh! You can touch it with a feather. See the purple gas that's here? That's iodine. And so this has blown a hole right through those papers. You can see that. And they were set off by a shock wave. Lots of fun to play with nitrogen iodide. All right, what you got next?
Well, I want to give a shout out to a few classes that are here.
Great.
So Mr. Visser's class in Athens, Mr. McMaster's class in Cornwall, Mr. Lesperance's class in East Maine, the classes from Francine Wesley Secondary in Kashechewan. Sorry, folks, I haven't been to Kashechewan, but I've been to Moosonee. And Mr. Lawton's class from Bell High School, as well as Mr. McCabe's class as well. Okay, and we'll do some more shout-outs later, but now let's make some slime.
All right.
Okay, so what do you need to make slime? Well, you need some polymer molecules. Okay, so polymers are, as the name implies, mer means unit, poly means many. And so a polymer is a giant molecule that's made up of many, many units. Okay, and so you can make slime in a variety of different ways using a polymer called polyvinyl alcohol that's often used in cosmetics. Or you can use it make it using a biological polymer like collagen, which is in all kinds of things, including glue. Okay, and catgut, like for strings and tennis rackets and squash rackets and stuff like that. Okay, and now what you need to do is you need to cross-link the polymers or get the molecules to interact with each other, because otherwise it's like floppy pieces of spaghetti flowing around. But if we can get something, if we mix in something that forces those molecules to interact with each other, then all of a sudden it becomes much stiffer and much more viscous. So you can see here, this is just some regular old wood glue here. And if you want, this is the sort of thing you can experiment with at home with different glues, and you might need to dilute the glue. And then there's borax laundry detergent. Okay, and you mix it in, and I just mixed in some green food coloring, make it look like snot. Why not? Okay, I know slime was a big thing a couple years ago. Like, there we go. So what the borax does is it causes the collagen in the glue collagen molecules to interact with each other, and we get a big pile of snot. Okay, so kind of reminds me of stuff that was coming out of my daughter's nose earlier this week. Dreaded daycare cold. Okay, so that's some polymers and slime / snot.
Snot, chemical element SN,
Yeah.
bonds permanently to corduroy. All right, Jamie, if you could switch to the overhead camera. I'm going to show the audience that I have a bottle of sodium. You'll see here it's labeled Na, so it must be sodium. Sodium is a metal. It's way over on the left-hand side of the periodic table. And I'm going to take out a chunk of sodium from this bottle. All right, there we go. So you can see it looks like a metal, kind of gray and dull. This is stored under oil for reasons that will become apparent shortly. The oil keeps it away from water. And sodium is a very soft metal. I can cut into it with a kitchen knife here, break off a piece. You can see the nice shiny surface of the sodium underneath, which hasn't been oxidized and is not covered in oil. That will react quite vigorously with water. And this is a reason that the police want to know, the firemen want to know what's in our labs, because if they come in and spray water on a fire, but you've got sodium exposed, well, they're going to get a bit of a surprise, which is not what we want for our firemen. So I'll put the big pieces back in the jar here and get the jar out of the way.
Would you like the lights down for this one, Bob?
Sure. And what I'm going to do is grab one of these pieces of sodium and I'm going to drop it into this graduated cylinder, which has about 10 centimeters of water in it. And you'll see that this metal reacts vigorously with water. If I put a piece of iron in here, it'll oxidize, it'll rust, but it'll take days or weeks. Not so with sodium. There we go. So it's hissing, making a bit of smoke. There we go. A flame and even a pop. So what's happened here is that the sodium has reacted with water. It has reduced the hydrogen in water to hydrogen gas, which then combines with the oxygen in the air above this cylinder and explodes because there's a bit of heat in there too. I've got another piece here, so let's get rid of that too. Safest way to deal with sodium is to put it in water. So that's hissing. Probably should have got Jeff to blow out that cylinder first. Oh, there's a bit of a flame. I saw a little bit of, there we go. Pretty amazing that a metal will react with water so vigorously. But this is the case for things that are on the far left-hand side of the periodic table. Sodium and potassium and rubidium and cesium and so on. Very reactive metals. Well, this one is still going. Sometimes it goes bang at the end. Ah, that's a great one. Come on, pop. Never seen one go on this long.
Yeah.
That's just awesome. That's just little bits of sodium reacting with the water. This morning we did one, it went bam, and we've got marks on the ceiling now. All right, whoop, there's one last gasp. All right, so that's sodium and water. One of my favorites.
What I have here is a solution of sodium acetate. So sodium acetate is used to flavor salt and vinegar potato chips, okay, because it's the sodium ion that's in there that actually gives us the salt flavor. But if you're going to have vinegar on your chips, right, well, you know, they'd be awfully soggy, and that's not really the way we like to eat potato chips. So if we have the sodium salt of vinegar, so sodium acetate, we get the salt and we get the vinegar flavor from the acetate ion as opposed to acetic acid that's in vinegar. Now, sodium acetate is interesting because it also exhibits a phenomenon called supersaturation. So what I have in here is sodium acetate and a little bit of water, and there's more sodium acetate in here than should really be able to dissolve. So if I put in even the tiniest little fleck, it's all going to come crashing out.
Ooh.
Look at that. It's all solid.
Pretty cool.
And it's a bit exothermic as well. It's nice and warm. Okay. Now, there's also a fun way we can do this as well. I got a little black light here. Okay. And now I've got a little bit more. I'll turn the lights down. Okay, worry about that later. Okay, and so you can see this kind of glows in the dark in this solution. Now what I'm going to do is I'm going to pour it in here, and there's some sodium acetate in the pan. Watch what happens as I pour. You can actually make a nice big tower of fluorescent sodium acetate. And now I'll be able to heat that up and let it cool and reuse it again tomorrow.
Nice one.
Yeah. All right, so you got another sodium demo, Bob?
I have another sodium demonstration, one of my favorites right here. I'm going to show you this lethal looking gadget. And over here, I have a jar of pickles, which we've used for this demonstration for many years. A testament to how pickling something can preserve it for a long time. I'm going to take out one of these. These are Strub's kosher pickles, naturally fermented, barrel cured. And I'm going to stick it on these two forks. There we go. So these two forks are about 1.5 centimeters apart from one another, and they're connected to a source of electrical energy. And that consists of this variac over here, which can give us up to 110 volts. So I'm going to turn this on. I'll get you to hit the lights if you would, Jeff. And I'll turn this up. And so we're putting 60, 70, 80 volts across this pickle, and then suddenly you get this glowing. This is why we call it the electric pickle. So that color is very indicative of something important, which is the presence of sodium. Whenever sodium is excited and then loses its excitation, it does so by emitting light in the visible portion of the spectrum, this yellow light. You've seen this before. The yellow street lights are sodium lights. They don't contain pickles, they contain sodium metal. So an electric discharge excites the atoms, and when they de-excite, they emit light in this portion of the spectrum. So take it from me that this doesn't smell very nice. This is not the way to prepare or eat a pickle. But that color is very important. You'll see that color whenever there's a fire because there's sodium everywhere. So when the fire burns, it excites the sodium atoms as well. So keep that yellow color in mind. All right.
Okay. All right. Before our next demonstration, we want to do a few more shout-outs. We got lots of schools here in Ottawa that have shown up. So we've got classes from St. Andrew School. We've got classes from Ms. Arthur's classes at Glebe Collegiate. You guys win the prize for being the closest school. For those of you that don't know, they're about 1.5 kilometers away. St. Leonard, St. Katari, the Ottawa Carleton Virtual School, St. Pat's High School here in Ottawa, St. Brother Andre, OMS Montessori, St. Peter, Mother Teresa High School, Canterbury High School. Out in Pembroke, we've got classes from Bishop Smith, and we've got some homeschool classes here too, as well as the folks from Walkerton, Ontario District Community School. So, great. Thanks for coming. We hope you're enjoying the show. We'll have some more shout outs too before we're done. But now, some of you, I don't think many of you remember wearing diapers, but you may have younger brothers or sisters or cousins, and you've changed a few diapers, and you ever wonder, how the heck does that stuff work? Well, here you go. So here I've got a beaker of water, and now I've got 3 cups here, and we're going to play a little game. Where's the water? Okay. So,
Woo! Nitrogen triiodide. There's a little bit left.
snap, crackle, pop, nitrogen triiodide. Okay, this one? Nope. This one? Nope. How about this one? Nope.
What the heck? I saw you put it in one of them.
Yeah, so how does that work? Well, what was in one of the cups already was something called a superabsorbent polymer. And now I'll show you how that works. So I'm going to put some more superabsorbent polymer in here. And so again, this is a very long molecule, but these superabsorbent polymers are what we call extremely hydrophilic. So they really like water. And in fact, they'll associate with it so much that what we can do is even put in, with what I put in there, I can easily fill this entire beaker and more. And now I just need something to stir with. I'll use my slime stick. And within about 10 seconds, it's completely gelled. And won't even tip over. So we just put that behind a fine cloth mesh, and you've got your diaper. Okay? Now, is a diaper completely filled with this? No, because if we filled the diaper with this, it could absorb so much water that the kid couldn't actually wear it because it would be so heavy it would just fall down. So that's kind of overkill. So it tends to get mixed in with a few other things like, you know, sawdust and things like that. Okay.
The baby would never wake up.
Yeah.
All right, I'm going to show you something a little more physical than chemical this time. And this has to do with radiation. What I have here is a small amount of uranium trioxide. Uranium is naturally radioactive. Not terribly radioactive, but naturally radioactive as it comes out of the ground. This has been refined and turned into this yellow oxide. And what I have here is a Geiger counter. And the function of a Geiger counter is to capture and register any radiation that it encounters. So this tube has a cap, which I'll remove, and a window here that radiation can penetrate. And inside the tube, radiation interacts with the gas and generates electrons, and the electrons are detected by the detector. So if there's any radiation coming out of this UO3, it will display on the meter, and you'll also hear the ticking here. So I'll get close to this. And you can hear that sound. Every little tick is probably a gamma particle, a photon, a high energy photon that's coming out of this right through the glass, through the uranium itself, through the glass, and into this detector. Now I want to show you that there are two ways of protecting yourself against radiation. If I put this here, you can hear the ticking from that. One way to protect yourself from radiation is to move away from the source. And the further you move away, the less radiation is going to impact you. It's called an inverse square law. The closer you are, the more radiation you're going to be exposed to. But the other way, which is quite common, is to put some mass between you and the source. So I've got a water solution here, and I'm just going to put that between the source and the detector, and you can see that the radiation almost disappears because now the radiation from the uranium is being absorbed by the water and the glass in this bottle. So remove that. The radiation gets to the detector, put something in, it doesn't. So the best thing you can do is put some mass between yourself and the source, but also move away from the source, and then you'll protect yourself that way. You probably had dental x-rays, and the technician goes into another room behind a leaded glass window to protect his or herself, and also puts a lead shield over your body to protect your body from the radiation. So in that case, both distance and mass are being used to isolate yourself from the radiation. So I thought you might find that interesting, especially if you live in northern areas where there is some uranium mining going on. This is how you're protected from radiation.
Okay, we've got an interesting question I think we can answer probably on the fly here.
All right.
Why does the radiation have a negative impact on us or substances?
Well, that's a great question because the radiation is very energetic. The photons that are coming out of that, or there's also alpha and beta particles, they don't get out through the glass, but if they did impact you, they're far more energetic than chemical bonds. So they can break chemical bonds, for instance, in your DNA, and that can cause mutations and that can cause cancer. So that's the main worry we have about radiation, is it eventually causing cancer if you're exposed to it for a long time. But if you protect yourself from it, you needn't worry.
Okay.
What do we got next?
Well, I think we're going to have a
bad breath contest.
Bad breath contest here.
All right. Jeff usually wins this, meaning he's got the bad breath.
Yeah. All right. My solution's still being a little pokey here.
Well, that's an interesting looking thing. Is that your 4-layer experiment?
Okay, so here we go. All right, ready?
Yep. So see that mine is pink and Jeff's is blue.
All right, now mine's blue. Really blue.
Now when we blow into this, we're blowing oxygen in, and we're also blowing carbon dioxide in.
Hey, wait a minute, I broke mine.
Hey, what happened?
Okay, I got my blue again. Oh!
Mine's still pink.
All right, I got a blue. Why does it keep changing? What did you do, Bob?
I think you better explain the chemistry of yours.
Yeah. Okay. So this one contains a dye called methylene blue, which is an extremely powerful dye. Powerful in the sense that it doesn't take a lot of molecules to get a lot of color. But it's also what we call redox active. So it has an oxidized form and a reduced form. The oxidized form is blue. The reduced form is colorless. And so also in the water there, I have glucose and potassium hydroxide, which combine will actually reduce the methylene blue to its colorless form, which we call leucomethylene blue. And I can convert the leucomethylene blue, the colorless form, back to the colored form with oxygen gas. So I can do that with either the oxygen that I exhale, or I can put the cap back on here and shake it, shake it, shake it. So that'll keep going back and forth for about a half an hour. Bob's running out of air here. He didn't get the pH right in his solution, I think.
I made mine a little bit too basic, and the acid in my breath wasn't enough to turn the solution acidic. So I'm going to cheat, and I'm going to add a bit of acid, but you'll see what happens to the color. And this is a reversible reaction. If I make it slightly acidic, the color disappears. So this indicator is pink when the solution is basic, but it's clear when the solution is acidic. And just like Jeff's reaction, reactions like this are reversible. So now it's acidic and it's clear. If I add a base, it goes back to the pink color. And that's because the indicator has two forms, one in base where the hydrogen are stripped off, and one in acid where the hydrogen are added to the molecule, in which case it becomes the other color. So those are acid-base indicators.
Okay.
Now
All
it's
right,
time for some layers.
Now, oh yeah. Okay, quick little Christmas demo over here. Okay, so here I have three things that I have mixed together. Okay, so I have some liquid, a silver liquid on the bottom, green in the middle, and red on top. So these are our nice Christmas colors. Okay, and what I like about this demonstration is now I can mix them up. And they separate out again. So this is what we call a triphasic mixture, 3 phases. So on top here I have toluene, which is an organic solvent, so it's hydrophobic, oleophilic if you like, so it dissolves in oil-like substances. Okay, and in there is a dye called Sudan 3 that gives it the red color. And then I've got a little bit of suspended solids in there that are sticking into the green layer, which is water that contains a little bit of food coloring to make it green. And also I made it green with some nickel chloride salt. And then on the bottom, I have our dear old friend elemental mercury, okay, which doesn't really dissolve in anything. So I can shake it up again and let it separate out, and I can do this all day. And I got 3 nice little Christmassy layers there. Okay. All right.
Nice colors.
Yeah, pretty colors. I like that one. All right, how you doing over there, Bob?
I'm doing well. In this demonstration, we're going to make a giant Christmas ornament. I've been heating up this flask with hot water. So we'll just get rid of the water here. The flask is still warm. And I'm going to put into this flask 60 milliliters. So there's 10, 20, 30, 40, 50, 60. That looks like about 60 of a solution of a sugar. Dextrose it's called. And the dextrose is going to act as a reducing agent for the silver ions which are dissolved in this solution. So this contains silver ions. I'm going to pour that in there and then stopper that and shake it around. And you'll see that the silver ions are going to come out of solution. They're going to become reduced, as we say, to silver metal. And while this is happening, the sugar is being oxidized by the silver ions. And gradually the silver will plate the inside of this flask and make us a nice Christmas ornament. So this is actually the way that silvering of mirrors and so on was done for the longest of time, by using silver. Jeff reminded me this morning that they now tend to use aluminum instead of silver. But this way you could reduce some silver ions onto the back of a piece of glass and create a mirror. So that's the sort of thing that's happening inside the flask right now. It just takes a minute or so to develop. I think you can see that it's starting to shine, this lovely Christmas ornament of ours. And this reaction is permanent. In other words, I could leave the silver on the inside of this ornament, but I can also strip it off with some nitric acid. Come on out here, Jeff, and we'll show the audience how nice and shiny this is.
Yeah, there we go. And if you can see the reflection off that, you can see it's pretty quiet in here. It's an empty room except for us and one camera person.
Yep, except for the thousands of you that are watching.
Yeah.
So it makes a pretty nice silvery coating on this. And as I say, I can strip this off just by adding a bit of nitric acid. The silver will go back into solution, and then I can do the reaction again. So that's our Christmas bulb.
All right. If you can get the lights for me, Bob.
I can do that.
Our next demo is another Christmas one. Just a second here. I'm going to just get this started while we're waiting for Bob. You can turn the lights off, Bob. All right, so another popular Christmas decoration would be candles. Okay, so I have a nice little candle here. And here's this is a fun one you can do at home.
Oh, Jeff, you can't eat a candle? What's the matter with this guy?
Delicious.
I think you're going to need to explain that one.
Okay, I'll explain. If you are what you eat, in order to do this demonstration, you have to be nuts. Okay, Okay, so what I have here, the base of the candle is a piece of banana. And then on top, I'm going to put a pecan, or a half pecan technically. Okay, and then nuts have a lot of oil in them, which is the oil from nuts tends to be very good, healthy food for us. But it also means that you can light it and it will burn for several minutes, in fact. Okay, and so if you light it like this, out of sight from other people, and then you walk into a darkened room, it's pretty tough to tell that it's not a real candle, especially if you have like a candlestick that's got a bunch of wax drippings on it or something like that. Okay, and then you just blow it out and take a good bite, including a bunch of banana so you don't burn your tongue. And there you go. It's the healthiest candle you'll ever eat.
It also works with most potato chips, by the way. The ones that are deep fried, which good potato chips are, the ones that are baked, they don't taste like potato chips. But the ones that are deep fried, they contain a lot of oil. Try lighting a potato chip on fire, you'll be amazed. All right, how about we blow something up? What I have here is a copper can, cylinder, a hole on the bottom, maybe 2 centimeters in diameter, and a tiny hole at the top, maybe a millimeter or 2. And what we're going to do is fill this cylinder with hydrogen gas. So I've got a cylinder of hydrogen here. And I'll put this up the bottom of this and we'll displace all the air out of this cylinder and fill it instead with hydrogen. As soon as I'm sure it's full. Sounds like it might be now. I'll put my finger over the top because hydrogen is a lightweight gas. Place it on the stand and Jeff will light the hydrogen coming out of the top. So you'll see a flame at the top there. I'll just get out of your way. I'll pull the hydrogen tank out of the way. Now what's happening is that the hydrogen is burning off the top, so that's drawing air in the bottom. So the mixture is getting leaner and leaner in the sense that there's less hydrogen and more oxygen and nitrogen as this flame progresses. And what will happen at some point is we'll get to what's called the upper explosive limit of hydrogen. And so this will make an interesting noise on the way down. Hasn't quite started yet. Is it still running? I think so. Well, there it goes. Hear that buzzing sound? So that means there's less and less hydrogen and more oxygen and air in there. Now lean forward in your seat and listen carefully. Sorry, I don't have enough of these to go around. Almost got them on in time. So if it wasn't loud where you are, I can assure you that was extremely loud in this small room. It's like a shotgun blast going off right next to your ear. We call that the hydrogen bomb. Whew. Oh. Never gets old.
Yeah. It's also great because we can scare the pants off people out in the hall.
Yeah.
All right. So now I'm going to show you another one that you can kind of do at home. Do you want to get ready for the next one, Bob?
Yeah, I want to find my...
Here you go.
Was it there? All right.
Fresh one. Okay. So, plain old laundry detergent. Okay. Gets your whites whiter and your colors brighter. Okay. And just to show you that this is what it's meant to be. Okay. I haven't altered it in any way. And now, little black light here. And, whoo, glow, glow. Okay, so there's a chemical in there that does actually make your clothes look brighter. And the reason it does that is because it absorbs UV light, which we can't see, but then it fluoresces. So it absorbs the light and then gives it off, and it gives it off in colors that we can see. Okay, and so as a result of that, your things actually do look brighter. Your clothing actually does look brighter. And we can use this fluorescence phenomenon in other ways in our lives, and we actually do. How's it going over there, Bob?
It's looking good.
All right.
So I've got a sign here that's, I can't really read very clearly here, but if I put it up to the UV light, the fluorescence becomes obvious. So I wrote on this with fluorescent ink pens, and you can see that they fluoresce in a portion of the visible spectrum, obviously, that you can see. Very difficult to see away from the UV light, but once you're up to the UV light, it's very clear. So it's the same idea. The UV light excites the molecules that are in the ink. They respond by giving off light in the visible portion of the spectrum, which you can see. And this is fluorescence. As soon as I take it away from the source of excitation, the fluorescence, the light disappears. It's only there for a very split second. That's different from another one that we're going to show you in a moment.
Okay. And for those of you that don't know, black lights, are often seen in clubs and bars. And one thing that you can have is a relatively common drink to have at such an establishment would be a gin and tonic. And what I have here is a bottle of tonic water. Okay? And so the tonic in tonic water is quinine. And quinine is actually a treatment for malaria, hence it's the term tonic. But quinine also fluoresces under UV light. So it turns this, it doesn't turn blue, it absorbs UV light and gets excited, but when it relaxes back to what we call the ground state, the light that it gives off is actually in the blue part of the electromagnetic spectrum that we can see. Okay, and so just to prove that this really is tonic water, I'm going to have a drink here.
Oh, geez, Jeff.
Oh, I shouldn't spill, especially on my microphone. Okay, so don't spill your gin and tonic if you're over when you're old enough and you're out at a bar. Okay, and by the way, it won't really protect you from malaria because you'd have to probably drink about 30 liters a day. If you drink 30 liters of water a day, you're going to wind up in the hospital with water intoxication. Okay, but that's a separate story. Over to you, Bob.
The next thing we're going to show you is a related phenomenon related to fluorescence. This is called phosphorescence. Same idea. An energetic light source in will excite some molecules. They'll respond by emitting visible light that you can see. But in this case, the light persists for a certain amount of time. You may have seen this in your TV remote control, which kind of gets charged up if you leave it out in the light. Then when you turn the lights off, the buttons continue to glow, so you can find it. So on these pieces of paper on the blackboard here, we've coated them with a phosphorescent compound. Now, I've got a red laser pointer here. If I swirl it around on these, nothing happens. And that's because red light is low energy photons. They don't have enough energy to excite the phosphorescent molecules. But in my hand now, I've got a blue laser pointer, and blue photons are much more energetic. So if I go like this on the poster, we can write on it, and you'll see that the fluorescent radiation persists for some time. So it's still seconds, and it looks like it's going to persist for maybe 10, 15, 20 seconds, something like that. So it's related to fluorescence, but fluorescence is immediate and phosphorescence is delayed. Jeff's got a better light to do this with, so you can flood it with it, and it stays lit up for many seconds.
So yeah, that's a UV flashlight, which are another fun thing. So it's a black light. My mic is dead. Oh, okay. I'm gonna have to come stand over here next to Bob because apparently I killed my mic with the tonic water. Oops. So yeah, these are UV flashlights. So they're fun. If you can, pick one up at a hardware store or online, and just take them around your house. I think they're a real they're a lot of fun to see what fluoresces.
You got to read this one.
Yeah. One of them at 395 nanometers, so just outside the visible range, apparently is great for making scorpions fluoresce. So there you go.
In case you have scorpions and you can't see it, you just shine this around and oh, there's a scorpion. What a bizarre product. So that's phosphorescence. I think Jeff has something to say about a luminous reaction.
Yeah, so...
And I have to follow you around now, do I?
Our next phenomenon is going to be a related one called chemiluminescence. So now we're going to do chemical reactions where instead of giving off heat as a product of the reaction, we're going to give off light. Okay, so 1, 2, 3.
Keep watching. Oh, there's the first one.
So the chemical that's doing this is called luminol. If you've ever watched CSI or related shows, you know that this can be used to pick up blood stains. And here we're actually using a reactant oxygen species to actually make it fluoresce. Not fluoresce, chemiluminesce here. So chemiluminescence is I gotta follow Bob, because he's still my microphone. Chemiluminescence is another phenomenon that we see most reactions give off energy as heat, but these ones give off as light.
All right. How about we blow something up? I'm going to leave this guy on. That's fine. So this reaction is one of my favorite. The flower pot on the bottom just contains sand, and that's going to catch the products of this very exothermic reaction, a reaction which releases an awful lot of heat. So inside this smaller beaker, I have sand around the outside, and the reddish mixture on the inside is iron oxide and very finely divided aluminum metal. And in this reaction, the oxygen is going to jump from the iron oxide to the aluminum metal. And the way we're going to make that happen is by taking a party sparkler and sticking it in there to use as a fuse. So the party sparkler makes very hot sparks because there's magnesium here, and it makes magnesium oxide. They're going to fall into the iron oxide aluminum mixture. That's going to start that mixture off. Then you're going to see something spectacular. We're actually going to create molten iron in a matter of seconds from a chemical reaction. So I'll just move some flammable things away here. Say when, Jeff. Go ahead. All right, so I'll light the party sparkler. Whoop. There it goes. One of those sparks will set off the main reaction. And then you'll see something pretty spectacular. And I want you to watch what comes out the bottom of the upper flower pot when that reaction goes. There it goes. Now out the bottom, there, coming out, that's liquid iron. So in a matter of seconds, a chemical reaction gave us enough heat that this thing melted the products, one of which is iron metal. And I'll show you the piece of iron metal. It's still quite soft. I can hardly pick it up with tweezers. So that's mostly iron metal and a little bit of aluminum oxide. The oxygen jumped from the iron oxide to the aluminum metal to make aluminum oxide. There's quite a big chunk of, there we go, molten iron. This is soft. I'm squeezing it with the tweezers here. That'll take half an hour to an hour to actually extinguish. Boy, that was a good one. So it's a question of how much heat is released and how quickly the heat is released. The bigger both of those things are, the higher the temperature will be, and in this case it was actually a high enough temperature to melt the product, melt the iron. So that's called a thermite reaction, and that can be used in the field to weld railroad tracks together. They would suspend this underneath the ends of two railroad tracks they want to weld together and set it off, and the liquid iron would fuse the two pieces of track together. No need for a welding machine. I love that reaction because so much heat is released in such a short time. Okay, Jeff?
Okay. So what we've got here is the first of our last two reactions. Now, before I start this, I want to send a shout out to our most distant schools. So we've got attendees from Sage Creek and Sergeant Park, I think it was, in Winnipeg. So that's fantastic. We've got attendees from Norman Wells in the Northwest Territories, and out in Nanaimo, BC. So we are really stretching the limits. We are really going, you know, we had attendees out in Halifax this morning, so we are pretty much coast to coast to coast in our coverage of the country, which is fantastic. We're really appreciative of the reception.
Yeah, thank you all for being here.
Yeah. Now, this last demonstration here is related to fireworks. So there's a lift charge, 3 parts to fireworks, a lift charge that lifts it up into the sky, an explosive charge that makes it go pow, and then there's a metal salt that's used to give off the color. The chemical that I'm heating up here is potassium chlorate, which is an oxidizing agent. And that one, it used to be used in the explosive charge in fireworks. It's not anymore, but it's a very good oxidizer. So here, what we're going to do is we're going to break down this peanut M&M using the oxygen in the potassium chlorate here, the same way our body would use oxygen to digest it over half an hour or so. Okay, so I'm going to put it in, and we're going to get through the chocolate and the sugar in there very quickly. And so the temperature is about 700 degrees, but inside that, once it gets through that, there's the peanut. And the temperature there is about 1,000 degrees as it burns through that. And that's why we do this in a little portable fume hood here, so we don't smoke the place out completely. All right, and how about a white hot peanut? Woo-wee. All right. So, we hope you've enjoyed our show. We have one more demonstration for you. And this one's a little more closely related to fireworks. So, now I'm actually going to excite a metal ion here, along with a fuel and an oxidant that's in there. Okay, I won't bore you with all the details, but on the right here I have potassium, which should be kind of purple. On the left is strontium, and which should be red, and then in the middle we have copper, which is actually going to give us a blue color, but blue color in fireworks is actually really tough to do, so watch out, because this one is really cool and it's really bright. Okay, here we go. Potassium. Okay, how about the strontium? Woo-wee. And copper. All right, that's our show, folks. We hope you've enjoyed it. Stick around for the Q&A if you want to. Tell your friends we're doing this again tomorrow for high schools at 1 o'clock and elementary schools at 9:30. So we're happy to take your questions. Thanks for coming.
Thanks for coming, everybody.
Thanks very much, everyone, and thank you, Jeff and Bob. That was a great presentation. I've been checking the Q&A, and we have one question that has, oh, no, there's just been a shout out from Norman Wells saying a large thank you very much. They really enjoyed the show. We thank everyone today for attending, and I'm seeing some questions come in. So here's one. Out of all of the fantastic experiments, which one is your personal favorite? That's either for Bob or Jeff to answer.
Go ahead, Bob.
Well, my favorite is the thermite reaction, I'd have to say, because that's a demonstration of how much energy there is in a chemical bond. To get that much heat in such a short time that you can melt iron from it, I just think that's a great demonstration of the power of the chemical bond. You must have a favorite.
Yeah, that was a really cool one.
I really enjoy the firework one there at the end. We've got some others that we really can't do indoors because they're a little too energetic or a little too stinky. One of my favorites that's like that is called the barking dog, which chemiluminesces, so like the luminol clock that we did there. Yeah, we've got way more than we can show you in an hour.
I love the next question.
Did you get good grades in high school science classes? Yes, but I certainly wasn't always the best student in the class.
Yeah, same with me. I'm no Einstein. My science grades were better than my English grades, I can tell you that much. But when you learn to love something the way we love chemistry, you get better and better at it. So by the time we got to university, I think they were probably our best grades, yes. Great question.
Yeah, but we weren't necessarily like the best students. We were in the top, probably 20-25%, but
Yeah, because we were always blowing stuff up.
yeah.
Well, I have a question, and that's about the fluorescence in laundry detergent. I suppose that the levels have to be safe to keep to keep that chemical safe from people absorbing it into their skin. Truth or fiction? It's just that I never realized that it was a fluorescence that was causing brightness.
Yeah, it's actually pretty. It's a pretty neat chemical. It's called umbelliferone, and the amount that's actually in there is actually really quite low, because the fluorescence is a really powerful phenomenon. You don't need a lot of chemical to get it to work well, and oddly enough, it's not that chemical is actually not that different from a lot of compounds found in foods that we eat. So it's actually not that different from anthocyanins and anthocyanidins, which are found in things like blueberries, and often give those color. We absolutely have to pay attention to toxicity of personal care products like that. But that particular one, I don't think is particularly concerning for that reason. It's pretty readily transformed into things that we're already accustomed to dealing with.
Good to know. Thank you. I suppose if I'm eating blueberries, I shouldn't be worried either. Moving on, I have a question here from someone, and you can see the Q&A yourself, obviously, but what sparked your interest in chemistry?
Oh, well, for me, that's easy. I had a high school chemistry teacher named Mr. Burton. So this would have been in the early 1970s. I'm sure Mr. Burton is long gone. He was an elderly fellow then. But he was so enthusiastic about his subject that it just infused into the students in the classroom, and several of my friends became chemists as well. So if you have a good chemistry teacher, you may end up being a chemist. If you have a good music teacher, you may end up being a musician. The teachers are a very important aspect of this. But also blowing stuff up, that's fun too.
Oh, same. I had some great science teachers in high school. In my case, my grade 9 and 10 science teacher was a guy by the name of John Hughes. Unfortunately, he passed away from a heart attack before I even finished high school. My grade 11 chemistry teacher was a guy by the name of Dennis Kreitzer, who also passed away from a heart attack not long after I finished high school.
Uh-oh.
Yeah, in my last year of high school, I actually had a bit of an exceptional circumstance where my teacher actually had a PhD in chemistry, and he was fantastic. So I had lots of talented people teach the chemistry courses that I took and science courses. They were very inspiring. That's a big deal, for sure.
I see another great question from Maya. Why was there a different color produced of fire for the last experiment for each element? Well, remember when we did the sodium experiment, that was the electric pickle. The sodium glowed yellow. But other elements glow a different color, and this is because the energies of the electrons in those elements are different. And that's because those elements contain a different number of electrons and a different number of protons. So all the energies are different, so the differences in energy between these levels are different as well. And the color that you see is a result of the difference in energy levels of the electrons inside the atom. This is in fact how we know what we know about the atom, by studying the light that comes out and interpreting that in terms of the energy levels inside the atoms. So that's a great question. We use these colors day in, day out to determine what's in a sample. If there's strontium, we will see the red light. If there's sodium, we'll see the yellow light, and so on.
Yep.
Great question, Maya.
Yep. Should you use hand gloves for safety? Well, when needed, yes. Most of what we did here today is, there's very little toxicity concerns with most of what we did. But certainly when we were mixing things to prepare for this, some of the things are a little more concerning. So yeah, we wore gloves for that. And in our research labs where we're working with considerably more concerning chemicals, yes, we wear gloves all the time.
Yep, I certainly wore gloves to prepare some of the solutions today. Not so much because they're toxic, but because they stain your skin.
And final question, because I don't see anything else coming up. If people wanted to make their own Christmas ornament with that silver, what was that stuff called? Could they do that themselves easily? Like, can you make your own Christmas ornament at home?
There are a few chemicals that we had to use to make this Christmas ornament that are a bit dangerous. So concentrated ammonia and a concentrated acid. The solution containing the silver itself is silver nitrate, and that can actually be purchased because it is a remedy for warts. If you put silver nitrate on a wart, it'll kill the wart. But the other chemicals in there are not things that I would recommend people have in their house. In fact, you'd have trouble finding them to buy them in the first place. So you'll have to leave that to us, I'm afraid, to make the big silver ornament.
Okay. All right. Are there any other questions? If there are no other questions, I think that it is time to say goodbye. It's been a great show, though. And again, I want to thank everyone for attending on behalf of the Faculty of Science, Carleton University.
Okay, we got some more questions coming in.
We got a good one here.
Yeah.
Good.
Okay, yeah, you got to take the next one, Bob.
Why can't humans see UV light? So at the back of your eyes, you have some receptors. And those receptors work by when a visible light photon comes in, causing the production of an electrical signal which goes to your brain. But the reason it works is because those photons are absorbed by the chemicals at the back of your eye in the so-called rods and cones. Ultraviolet photons are very energetic, and so they have an energy much greater than the energy difference of electrons in the molecules in your rods and cones. So those photons are not absorbed by your eye, and therefore there's no signal generated. The same is true at the other end of the spectrum, in the infrared portion of the spectrum. Beyond red is what infrared means. You can't see those either because they're too low in energy. So humans are basically blind to what's going on in space. There's this very narrow region of what we call visible light that we see, but there's infrared, and then on the other side there's ultraviolet and X-rays and so on that you can't see either. We're almost blind to what's going on in the universe. Very interesting question.
Yeah, you know who can see UV light?
Who?
Bees.
Bees?
Bees.
I didn't know that.
UV is actually referred to as bee purple. And if you actually look at flowers under UV light, you can see that there are actually veins of UV fluorescence in the petals of the flower. And it's sort of like, for the bees, it's sort of like directional arrows, like, come on, land in here. It's like the landing lights on a runway. And so yeah, flowers have evolved to attract bees to pollinate them that way, using that UV light, because bees are one of the few creatures that can actually see UV light that way.
Great question, Vicki.
Yeah, and then this one I think hits for Bob too here, the memorizing the periodic table.
Well, the way to memorize the periodic table is to come to Carleton University when you finally get to university, because I teach first year, and at the end of the first term in first year chemistry, I invite my students to come down to the front of the class, turn around, and sing the periodic table to the students in the class, which is terrifying for most of them, but maybe a dozen of them have the courage to do it, and for that they get 1 extra mark in the course. So it's only 118 words. I mean, I'm sure you've memorized poems that are much longer than that. Come to Carleton and we'll show you how to do it. Good question.
Oh, another one.
How many experiments did we do today? 24.
Yep, 24.
24 or 25, depending on how you want to count. So the bad breath experiment, if you count that as 2, we did 25.
We have probably 40 or 50 experiments that we do in rotation in these shows, but the ones we did today are the more popular ones.
Where do we buy our lab coats? I'm assuming that's what you mean by shirts. We found them online at a retailer that no longer sells them, unfortunately. Otherwise, I would tell you where, but somebody asked us before, and I went and checked, and they don't sell them anymore.
But if you Google tie-dye lab coats, I'm sure you'll find something.
Yeah.
They are epic.
Yeah, we think so too. Thank you.
Well, I don't think I've ever had an article of my clothing called epic.
I have, but you've seen my
yeah.
collection of Christmas sweaters.
Oh, yes. Well, that's great, everybody. Thank you for your questions. They were excellent questions, very probing.
Yep. All right. If there are no more questions, well, we'll say goodbye and thank you.
Yep. Come again.